All right, so as I mentioned just a second ago, the tests are graded. So your grade is posted in the WebAssign grade book, right? And so I don't know where you can find that there. Does it show up here or do you have to go to my total to see it? So, all right, so click on my total and you can find that, okay? And your my total is updated, so that is your current course average there. So of course mine is very low because I didn't take the test, right? So I haven't done any homework. So but yours will be higher than that, right? So up until now that number has just been reflecting your homework grades, right? But now it's got the test grade in it, so it's a much more significant figure, right? I mean, it's much more meaningful now what your grade average is there, right? So you want to start paying attention to that now for the remainder of the semester, so you'll know where you're at, okay, in terms of your letter grade, right? Also, you'll notice that Flux Dollars has appeared also, and but it's not clickable there, right? So this is how I know to get to Flux Dollars, but there may be another way that's easier. If you click on my total, right, and then scroll down a little bit. So there's where your test score is recorded, right? And then scroll down to where it says raw scores and click on that, and it will open this window, and there will be your Flux Dollars. Okay, so underscore is what your Flux Dollars are. So several of you have now collected Flux Dollars based on either turning in that extra credit assignment or the grade you made on the test, or some of you have also gone to the Math Center. All right, so so you may have a Flux Dollar total there, right? So that's how I know how to find it. What? Yeah. What, Emil?
Oh, no, I just saw the class average.
Okay. Yeah, so I can tell you what the class average was, but I think does it not show? Yeah. Yeah, the 200 is meaningless, so just look at the number. It shows you a number, right?
Yeah.
I think it says 27. 25. Okay, yeah. All right, so 25 is that's the key number, right? Okay. So see, Jad has 25 Flux Dollars, so that's very good because his attendance has also been very good. So that means he's looking at, if he continues that, 25 extra Flux Dollars there. So that's already 50. That's already 50, right? So if Jad continues to do well on his exams, then he's going to easily make the 75 that's necessary to test out of the final, okay, for instance, right? So if that's his goal, then he's well on his way toward matching that goal, right? Okay. But remember, the Flux Dollars also, you can purchase midterm points, right? So you can get points on these midterm tests. So if you did not make a good score on this midterm test, but you have a lot of Flux Dollars at the end of the semester, right? You can purchase bonus points to help make up for that that deficit, right, on one of the tests. Okay, hopefully just one of the tests, right? Because if you're making bad on all the tests, it's going to be hard to get enough Flux Dollars to work your way out of that, right? I'm getting ready to pass the test. Don't worry about it. I'm going to show you the test, right? So I'm going to pass those out for you guys online. You can look at your test score now, okay, in WebAssign, right? Okay. Then I have something else to say, because the sort of the nature of the class is going to change at this point, right? Depending a little bit on your test score. Okay, so I'm passing out tests now, so I'll wait a minute online. Alexander's online, right? Christian, I don't see. Ando Mencia, is he here or is he online? Muhammad and the other Muhammad. Oh, so all I see here. Yeah, it's online. So The other Fernando. He did. Self-trained. And roll backwards. Which is a real. Now is on. Right. On there, right. On. Just there. Out. Turn. In the blue line, right? Everyone should get one. All right. See you after class, right? Okay, so I do have some people that I see online that did not take the test. Okay, so the consequences of that are severe because you're going to have a 0. So you're going to get a 0 in your grade book, right? Okay, and I don't know what to tell you. All right, okay, going to be a 0. If you had contacted me, after the test or before the test and said I couldn't take the test today, then there might be a different story. But now it's too late, so that's going down as a 0. The answers are posted now in the Blackboard. So if you go to, if I can find it here, if you go to Blackboard right under test answers, that folder, there they are. Okay, so there are the solutions. So I highly recommend now that you take your test and try to correct your mistakes, right? So if you need help, of course, the test solutions are there, but you should try to correct your mistakes without looking at the test solutions first. Okay, and then if you just can't figure out or are not comfortable with what you're doing, then look at the test answers. Okay, so save that for save comparing your answers with the test answers till the end. There were a few instances now where, not many, but there were a few instances where people did not show work, and though you got counted off for that, right? If it was something where I expected to see some work, you did get counted off, so you were not the only one in the class that lost points for that. Okay, so I warned you about that explicitly numerous times. So on test number 2, do not make that mistake again, right? Okay, you're going to have to write something down on most problems, not every problem, but on most problems, write something down to justify your answer. Okay, even if you think, oh, I can do this in my head, I need to see something written down. So you need to translate what you're doing in your head onto paper, okay? So that I can be certain that indeed, right, you had it in your head, right? Okay, what procedure you were following to solve that problem. Okay, now. Okay, so you guys know now online, right, that your situation now possibly has changed. So if you did not make a 70 on this test, right, so not a passing score on the test, you can no longer attend online. So you need to come to class, right? So I'm expecting you guys can hear me there, right? Okay. So if you did not make a 70 on the test, for now, you've lost the privilege for attending online. This is not really an online class, right? This was published as a face-to-face class. So you will, and the attending it on Zoom is a privilege. So unfortunately for some of you, you've lost that privilege. You can earn it back now by doing well on test number 2. You can go back to attending on Zoom, but in the meantime, you need to come to class. I'm not doing that as a penalty. I'm doing that to save your grade, okay? Because if you're not passing on, if you're not able to keep up with the material and pass on Zoom, your only hope of passing will be to come to class, okay? So this is to save your semester. It's not to punish you, okay, for your score. You need to come to class. If you cannot do that, I don't know what to tell you, all right? Because I'm not going to count you as present, right? Even if you're attending on Zoom, I'm not going to count you as present. But I can guarantee you, you're not going to be able to pass the class, all right? It just won't happen. I know this from experience. So you really need to, no, it's nothing. The only thing that's in the syllabus is if you do not make a passing grade on the test, you must come to class, okay? So, so you got to come to class, all right? If you did not pass, so, okay. All right, so for many of you, I expect to see you in class, and I will welcome seeing you in class next time, okay? But for those of you who did fine, you can continue attending, and that's several of you, you can continue attending on Zoom, okay? Until test number 2, right? If you plug test number 2, then you're gonna have to start, then you're gonna have to start coming to class before test number 3, okay? That's just the way it works. For your benefit and safety, okay? Y'all have questions about what I just gave you back, or what's in WebAssign? Probably haven't had a chance to look in WebAssign yet. Emil.
At least 2 more attempts.
Yeah, so right, so just look at the syllabus. There's 3 tests, right? Okay. So so you just finished test number 1, so you got 2 other midterms plus the final exam. Yeah. Okay, right. So 3 tests plus the 3 tests plus the final exam. All right. I don't know what April 6th means there. Oh, when is the next test, right? Okay. Yeah, schedule for April the 6th. So we're a little bit behind schedule. We'll see if we'll make the April 6th date, or we have to, but we have some time to think about that, right? So, and also we have spring break is in the middle of this also. So week after next. So, okay. All right. So, so done with test number 1, at least. I think now probably what, if I would give you advice, right, on for test number 2, then since most of you are participating in the homework, that's good. So continue doing that. If you have not been participating in the homework, of course, you need to up your participation in the homework, right? And then I know probably then you did not prepare for the test by going over the sample test carefully. All right, so you did not go through the sample test. I think you'll realize after having had the test, right, and looking at the sample test, that would have benefited you greatly. So for test number 2, you know, don't make that mistake twice. Now, third is you guys are not taking advantage of tutoring, and so you need to go to the math center more, okay? And also, if possible, find someone to study with from the class. All right. Now it's been a little bit hard to get to know each other because of the pandemic and social distancing. So we cannot, unfortunately, work together in class as much as we would in groups. Okay. But if you possible, find someone in the class to work with or to study with, especially in preparing for the test, that will benefit you tremendously. Okay. So actually, that is the number 1. These things are closely observed, closely studied. Studying in groups is the most effective technique for passing classes, right? So if you have that opportunity, then please do that. Okay, take advantage of that. So that's my advice for test number 2, in addition to, of course, coming to class, right? That really will, I know you got to drive and maybe or get on the bus, and gas is expensive now. I understand that, but it's not going to be more expensive than not passing the class, and it really will benefit you. I've seen it multiple times. Okay, so I'll see you guys Monday. All right, but we still have work to do today, of course. So do you have other things that you want to ask there about where we're at?
I want to ask about how do you get access for the Flux Dollars?
Well, so that's in the syllabus, right? So how do you get Flux Dollars? That's in the syllabus, right?
No, I mean, how do we use that, or we just?
Oh, at the end of the semester, you'll get a shopping cart, and then you get and then you get to choose how you're going to spend your Flux Dollars, right? Okay. All right. So, but you can look at the syllabus now and see what your options are. Okay. All right. So I've got a little bit of let's go ahead and switch to the notes. We do have a homework assignment, but so this is on trigonometry of right triangles, right? And so I moved that back. It was due Wednesday. So if y'all were working on that diligently, that's good. I moved it back a little bit here till Saturday to give you a little bit of time to finish it, since we just did the test. And speaking of that, I'm going to post probably a new homework assignment today, but not yet. And so speaking of that homework, though, and that topic, let's try a little bit of recall here, because now we're 2 or 3 days from having done this, right? Okay, so you will need a calculator for this one. So if you got your calculator, you can use that. Now, in this case, you can use your phone, right? Because we're not on a test, so you can use your phone as your calculator. So here's our recall practice. So for you guys at home too, right? We're just going to do a little solving of triangles here. That's what this process is called. So there's a right triangle, and one of the acute angles in that right triangle is 50 degrees. It's like you've got a length of one of the sides there, and we want to know the length of the side A. Okay, so how long is side A? All right, so see if you can remember your trig ratios, right, and figure out there the length of side A, but you will need a calculator for this problem. So remember, this is just recall practice. So just remember as much as you can. Can't remember, try to see if you can at least remember where you put it in your notes, right? Okay, I'm gonna lower the screen now. So I can write, did y'all make some progress on that? Do y'all recall some of that? All right. Or was that, have you already forgotten that? Because this is gonna be in that trigonometry of right triangle homework. So really useful to remember that before you start working on the homework. Okay, so do y'all have some suggestions on what I should do? Any ideas on finding this problem? Use what? All right, so someone says use cosine here, so I'm certainly willing to do that. So what expression would we write down there involving cosine? We write down what? Cosine something. Oh, yeah, it's gotta be, obviously gotta be 50 degrees, right? Okay, I guess we could use this angle too, right? But because we also know what this angle is. What's this angle going to be if this one's 50? What? That one's going to be 40, right? Because these two have to add up to 90 to match this right angle here. But that's kind of getting away from the main point here, right? We don't need to use that angle because we can work right with the 50 degrees. So what is the cosine of 50 degrees in this picture? What? A over what? 10, right? Yeah, A over 10, sure. Okay. Because cosine, remember, is in a right triangle, it's adjacent over hypotenuse, correct? So the adjacent side to this 50-degree angle is A, right? The hypotenuse clearly there is 10, so we have A over 10. And now we just have to solve this equation for A, which is easy to do. Just multiply both sides by 10. So you get 10 times the cosine of 50 degrees is what A is equal to. That's actually the exact answer for A. But, you know, normally you would want a decimal approximation, right? Because you'd like to know how long A is, right? Who knows what the cosine of 50 degrees is? So, so there's where our calculator comes in handy, right? Approximately what is the cosine of 50 according to the calculator?
6.4.
0.64. And so, so that means when we multiply there, right, A is going to be about 6.4. Okay. Hey, all right. So do y'all remember that? Could we have used some other trig ratio? I don't think so, right? Okay. Don't see one that's, I mean, with the 50 degrees, right? Okay. Couldn't use sine, right? Because we would have to know the length of this side, right? The opposite side. Couldn't use tangent, right? Because we have to know the lengths of the opposite and the adjacent side. We don't know either of those, correct? Right. So looks like we're pretty limited here to cosine. I guess we could have used the inverse of the cosine. What's the inverse of the cosine? What's the reciprocal of the cosine?
1 over cosine?
Yeah, that's 10 over A. Yeah, it's 1 over cosine, but that has a name. What's the name for 1 over cosine? The reciprocal of the cosine. That's one of the trig ratios.
Cosecant?
Think again there. It's secant, right? Yeah. So the reciprocal of the cosine is the secant. It's the reciprocal of the sine that's the cosecant. I know it sounds like the reciprocal of the cosine should be cosecant, but that's not the way it works. All right. So so we could have used secant, but probably that's not a key on your calculator, right? So this would be more difficult to use than cosine. All right. So anyway, so about 6.4. Okay. Well, you're going to have lots of opportunities in that homework that's due to solve triangles, okay, and also some applied problems also with triangles as well. So you want to work on that quickly, right? So that of course it's due on Saturday. So, but we won't have another chance to talk about it. So before it's due. So be working on that so you can send me questions if you have questions about problems. All right, so I'll have time to answer. If you send them to me on, 9 o'clock on Saturday, probably not going to see that. Okay, so let's scroll back up here in the notes now. And what we're really doing, we're sort of past this solving right triangles. We're now extending trigonometry to angles that are the trig ratios to angles that are not acute angles. So angles bigger than 90 degrees or negative angles. And last time we were discussing how to do that, and we're going to continue that today. But remember the idea, if I can find it here. Yeah, I gotta scroll way up here to remind you of just what the basic idea was. Gosh, this is a so the basic idea for finding the trig ratios for any angle of any size, so not just between 0 and 90 degrees, like angles you would find in a right triangle, but angles, again, bigger than 90 degrees, or say negative angles, right? Okay, remember the scheme that we were going to use is we would draw that angle in standard position. We would draw that angle in standard position, so that means that the initial side is along the positive side of the x-axis, and then the terminal side is going to be somewhere here, somewhere in your rectangular coordinate system, right? So you would draw the angle in standard position, and then on the terminal side of the angle, you would pick off a point, okay? It could be a point anywhere on the terminal side. So it could be close to the origin, or it could be far away from the origin. Any point will do, okay? So you pick a point off of the terminal side, and then you measure the distance from the origin to that point. That distance we usually refer to as r, okay, for radius, all right? But it's just the distance from 0, 0, the origin, to whatever point you picked off the terminal side of your angle, okay? And then you use the coordinates of that point plus this value r to define sine, cosine, tangent, etc. All right, and that is contained in this. How you do that is contained in this table. Okay, so the sine of your angle is going to be the y coordinate of the point that you choose divided by this distance r. Remember, you can compute this distance r by using the distance formula. And when you use the distance formula, that distance calculation simplifies to just the square root of the squares of the coordinates of your 2 points. All right. So here's our definition for sine of our angle. It's going to be the y coordinate of our point divided by the square root of the squares of the 2 coordinates of the point, right? Okay. Here's how you find cosine. You take the x coordinate and you divide it by r. Here's how you find tangent. You just take the y coordinate and you divide it by the x coordinate, right? And this scheme works for any angle, no matter how big or small the angle is. You just draw the angle, and then you have to pick a point off of the terminal side of the angle, right? And then just do these computations, and you can compute sine, cosine, and tangent, plus the reciprocal trig ratios, right, for any angle whatsoever. So it doesn't have to be embedded in a right triangle. So we've kind of freed our trigonometry, right, from right triangles, okay? So trigonometry now has become a subject through this mechanism, can become a subject that's a little bit broader than just the study of right triangles. All right, now the problem with this method, remember, though, okay, is it's a little bit clumsy, right? Okay, because you have to be able to pick a point off of the terminal side of the angle. So you have to draw the angle, and then you have to pick a point off of the terminal side of the angle, and then do the calculations. Well, the calculations are not that difficult, but it's picking the point off of the terminal side of the angle that's the tricky part. Okay, that's not always easy to do. So we need to simplify this process, right? And that's what we're going to do today. I'm going to show you how to find these trig ratios without having to really pick that point off of the terminal side of the angle. Okay. All right. Before we do that, though, I want to go back to that sheet that I gave you. Remember this sheet that has the trig formulas? I'm sorry, the trig ratios for the special angles. All right, so that's in table form here. All right, that's in table form. And then on the back is the so this is also posted on the Blackboard page for you guys at home. I'll show you where it is because I'm going to open it right now. But there's a kind of a geometric version here of the special angles. You know, the special angles, pi over 3, pi over 4, pi over 6, right? Pi over 2, etc. There's this sort of a picture of the special angles, and so this picture shows how you can use this scheme, picking the point off of the terminal side to find the trig ratios for not just the special angles, but also multiples of the special angles that are bigger than 90 degrees. Okay, so I'm going to show you the table here in just a second. Explain how the table works. It's pretty easy to understand. I just wanted to see that. Okay, let me open that from see if I can find Blackboard again here and open that. I think I put that under that sheet, under a PDF of that sheet under class notes and videos, but you have to kind of scroll down to the, there it is, okay, to that day where we were where I first passed this out. So there's the PDF of this. So of course, the first page is just the that's just the table form, right? Okay, of the sine, cosine, and tangent, right? Of the special angles, and then also the special multiples of the special angles that are larger than 90 degrees. Okay, that's what fills out the rest of the table. But here is kind of that same table in this sort of picture form, right? In this sort of graphical form. So notice in this table, what they've done here is they've just drawn pictures of the special angles, right? Okay, so here's pi over 6, and there's 45 degrees, right? And there's 60 degrees, and then here's 90 degrees, and then here is 120 degrees, right? Which is also that's also a special angle because that's twice 60 degrees, and there's 135 degrees, right? Which is 3 times 45 degrees, so that's a special angle. There's 150 degrees. There's 180. Right, and then so on and so forth, right, all the way around for one full revolution. Okay, now in this, so they've just drawn pictures of these angles, right? And remember, think of the initial side of this angle as being along the positive side of the x-axis. So these spokes here in the wheel, these are terminal side of these angles. Okay, and now, what they've also done, however, for you is they've superimposed a unit circle here on this picture. So this big circle that goes around, that's a unit circle. That means the radius of that circle is 1. Okay, the radius of that circle is 1. So all of the points on this circle are distance 1 away from they're distance 1 away from the origin. Okay, all right. So what this how you would use this table is, really don't even need it once you've seen it once, okay, is what this table is telling you is, look, for the angle pi over 6, which is 30 degrees, right? That's this angle here, okay? A point on the terminal side of 30 degrees is this point, square root of 3 over 2 and 1/2. By the way, square root of 3 over 2 is about 0.87. 0.87 approximately. It's actually 0.866 something, but approximately 0.87. Remember, that is more than 1/2. Okay, that's bigger than 1/2. That makes sense, right? Because look, in this point, obviously the x coordinate here is bigger than the y coordinate, right? And it's that much bigger, 0.866 versus 1/2. Okay, but the point is this point is on the terminal side of this angle, right? This point's on the terminal side of the angle pi over 6, square root of 3 over 2 and 1/2. So how do you find, for instance, the sine of 30 degrees? What would you do? Remember from the chart, sine of 30 degrees is which coordinate? Y divided by what? R, right. But what's the R always here in this picture, Robbie? 1. Yeah, it's always 1. So you can sort of forget about the R and just look at the Y coordinate there, right? Okay, so you can see that the sine of 30 degrees is 1/2. Okay, what's the cosine then? It's the X coordinate, right? Okay, which is square root of 3 over 2, right? Now, what do you notice about all of these? What do you notice about all of these coordinates for all of these points all the way around this circle? They're all the same numbers, right? You only have what? Square root of 3 over 2, right? And 1/2, and then what's the other value? Square root of 2 over 2, and then, of course, 1 or 0, right? Okay, so that makes sort of this picture easy to recall, right? Because the coordinates for these points, are always either 1/2 or square root of 2 over 2 or square root of 3 over 2, right? Okay, so look, blind yourself here slightly. If I said, what's the cosine of 120 degrees, which is 2 pi over 3 right here, correct? You would think, okay, I got to find the coordinates of this point, right? But I know the coordinates of that point are going to involve what numbers? Because all these coordinates involve just what numbers? We just mentioned what? Yeah, 1/2 square root of 3 over 2 and square root of 2 over 2, right? Okay. But now for 120 degrees or 2 pi over 3, what coordinate should it be? Well, 2 pi over 3, let's look. That is further up the y-axis than it is along the x-axis, right? So the y coordinate is going to be bigger than the x coordinate, right? Does that make sense, Emil? Right here? So you can just immediately tell yourself, oh, the y coordinate has to be bigger than the x coordinate. So that means that the two coordinates cannot be the same, right? So y coordinate must be square root of 3 over 2 and the x coordinate must be half. Then you're in business. Now, but you've got to get the signs correct also, right? You're in the second quadrant. So what would the signs be? The x coordinate would be positive or negative? The second coordinate. It would be negative, right? The y coordinate, what? Positive. So you would know, oh, this point must be minus 1/2 square root of 3 over 2, correct? Right? Okay. And then you know what the sine and cosine. So it's kind of easy to remember the points on this circle, and therefore it's easy to use the circle to remember sine and cosine for special angles. Remember, this is only for special angles, correct? Right? So if I ask you, what is it for 7 pi over 4, which is going to be down here in the fourth quadrant, right? 7 pi over 4. For 7 pi over 4, the x and the y are the same, right? The x coordinate and the y coordinate are the same. That's a 45-degree line. So if the x and y coordinate are the same, they must both be what? They can't be 1/2 and square root of 3 over 2, right? So what? Yeah, square root of 2 over 2 and square root of 2 over 2, right? Okay. So then you would immediately know, oh yeah, I know what the coordinates for this point have to be, right? Now, of course, the y coordinate has to be negative because you're below the x-axis. So remember, the sign there is negative. And now you can easily know what the sine and cosine are, right? They're both. Well, the sine is what? Minus square root of 2 over 2, minus square root of 2 over 2, right? And the cosine is square root of 2 over 2. Okay. How do you find tangent? With that sine divided by cosine, right? Okay. So if you know the sine and the cosine, then you'll be able to calculate tangent, right? You really only need to know sine and cosine. Okay, so this is sort of how this is why I gave you the second version of the table. Okay, some people find this easier to look at and use to remember the sine and cosine and the tangent for the special angles. This is only the special angles in this picture, so you can't use this to find sine and cosine at 50 degrees, right? Okay, not going to be helpful there. Okay, so there's the picture version. Here's, of course, just the table, okay? And I also discussed how you can remember the columns in the table as well, right, for sine and cosine. So you've got lots of little, at least a couple of little mental tricks there for helping you remember the sine and cosine for the special angles. You really do need to recall those. All right, well, now let's get back to where we were, and let's talk about in general computing sine and cosine. So let me scroll back. All right, so let's do it for some angles here. So 5 pi over 3, okay, all right. You should have memorized this one because 5 pi over 3 is a special angle. All right, 5 pi over 3 is a special angle, isn't it, right? Okay, if you draw 5 pi over 3, there's the picture. There's the picture. Okay, so you're going to end up there slightly into the fourth quadrant, right? So what point now, without looking at your circle, what point do you know is on the terminal side? See, Roddy, you look, I saw you look, cheated. Okay. Yeah, without looking at the circle that I just gave you, what point do you know is on the terminal side of this angle? It's got to be 1/2 square root of 3 over 2, square root of 2 over 2, square root of 2 over 2, or square root of 3 over 2 and 1/2, right? Okay. So this is not a 45-degree line. So the x and y coordinates are not going to be the same, right? So Sonny, which is bigger here? Is it the y value bigger or the x value bigger? Yeah, so what is this point then? What's the x value going to be? It's going to be the smaller value. 1/2, right? See, you've already learned it. And so what's the y value? Perfect, right? Square root of 3 over 2. But we're in the fourth quadrant, so we have to adjust the signs. So what sign is negative here? The y value. So now we're done. See, finding sine and cosine is so easy. What's the sine of 5 pi over 3? Sonny? There you go, negative square root of 3 over 2, right? And cosine is the 1/2, right? So you see, you knew that already. Okay. Now, let me show you the second way of doing this, okay? Because this works great for special angles like 5 pi over 3, but not all angles are special angles, all right? So let me show you the alternative way, all right? We're now going to compute what is called a reference angle, okay? So we're going to use the reference angle version of finding sine and cosine, right? So what I'm going to show you now is what's called a reference angle. So once you've drawn your angle, your original angle, right? So there's the 5 pi over 3. What you want to do is use the terminal side and find the angle between the smallest positive angle between the terminal side and the x-axis, okay? So you want to go from the terminal side and draw a positive angle to the x-axis. Make sure you do it in the most efficient way possible. You want the smallest angle between the terminal side and the x-axis, but it's got to be positive. Okay, so make sure you draw it positive. So in this picture, that's pretty easy to see, right? There's the terminal side. So I'm going to draw this angle up to the x-axis, right? I'm going to draw that angle up to the x-axis. That's called the reference angle for my original angle theta. Usually we denote that by putting a bar over the name of the angle. So that's why I have a theta with a bar over it here. That's just notation for reference angle. So what is the reference angle here? All right. So there I have it drawn, but what is it? So what is this angle from this terminal side up to the x-axis? See, the angle was 5 pi over 3. So what's this leftover part here? If you went one full revolution, how much would that be? That would be 2 pi, right? Or 360 degrees. So take the full revolution and subtract off the 5 pi over 3. Pi over 3, right, comes out to be pi over 3. Isn't that pretty obvious, right? If you're at 5 pi over 3, if you went another pi over 3, that would be 6 pi over 3. And how much is 6 pi over 3? That's 2 pi, okay? Yeah, so you see if you went another pi over 3, you would have gone 2 pi, which is 1 full revolution, all right? I don't really like you to compute the reference angle like this by subtraction, which you can do, but think of it as from the picture, okay? So I was at 5 pi over 3, and I need to go another pi over 3 to make full revolution there, right? Okay. All right, so there's our reference angle. So what do I do with the reference angle? Notice the reference angle is pi over 3. That's between 0 and 90 degrees. So when you compute reference angles, you're always going to get angles between 0 and 90 degrees. And we're very familiar with angles between 0 and 90 degrees. That's the point here, okay? So we really have memorized most of the things we need to know about angles between 0 and 90 degrees. And it turns out that the trig ratios for your original angle will be the same as the trig ratios for your reference angle, except for the sign. The sign might be different. Okay. Now, what about here? You know, sine of theta is going to be what sign? Positive or negative? See, there's sine, there's theta, right? Theta ends up in what quadrant? Fourth. Sine is what sign? S-I-G-N in the fourth quadrant. Negative in the fourth quadrant, right? Okay, so you know that sine of theta has to be the negative of this, okay? So sine of theta is minus the sine of the reference angle. What's the reference angle? We just said it was what? Pi over 3? And have you all memorized what the sine of pi over 3 is? Hope so. It's square root of 3 over 2, right? And so it's going to be negative. So we got the answer we were expecting, right? We knew that the sine of pi over 3 was minus the square root of 3 over 2, right? Okay, got the same way by same thing by using the reference angle. What about cosine? Of course, we know that's going to turn out to be 1/2, but we know that the cosine of theta is the same as the cosine of the reference angle, except what might be different? The sign in front. So you have to adjust that. But cosine in the fourth quadrant is cosine positive or negative? It's positive, right? So you don't have to adjust the sign. And so you know that the cosine of your original angle is the cosine of pi over 3, which is 1/2, isn't it, right? Okay. So which of course we already knew from before. So the value of using reference angles is, notice that we can reduce the problem always of finding the sine or cosine, and then same thing for all the other trig ratios. We can reduce the problem to only, it gives us a way of reducing the problem to only between 0 and 90 degrees. We can always reduce the angle from just between 0 and 90 degrees. So we really only have to know things, trig ratios for angles between 0 and 90 degrees, okay? That's really enough knowledge to find trig ratios for all other angles as well. Let's try another one. So let's try 210. So you're going to have to draw a picture. Once you've done this enough, though, you'll get really good at doing this mentally. So you don't have to draw as many scratch pictures. But scratch pictures are always good. So don't be shy about drawing them. Mathematicians certainly aren't. They'll scribble things down like this all the time. Okay. All right. So there I've drawn 210. 210 is slightly past 180, so it goes a little bit into the third quadrant, right? It's a little bit bigger than 180. Remember, 180 is a full open angle, so 210 is a little bit more than that. And now let's find the reference angle. So remember, the reference angle is the positive angle between the terminal side and the x-axis. So that's going to be this angle right there, okay, between the terminal side and the x-axis. Make sure you draw it positive. Don't draw the arrow backwards because that is negative. So there is a picture of theta bar. But of course, now we have to really know what theta bar is, right? So what is that? 30, right, sure. Because you went 30 degrees past 180, right, to make the 210. So your theta bar is 30 degrees. Your reference angle is 30 degrees. All right, so what do I know now? So I know now that the sine of 210 degrees, my original angle, is the same as the sine of 30 degrees, except I have to maybe adjust the sign. And do we have to adjust the sign here? You're in the third quadrant. So what is the SIGN of sine in the third quadrant? It's negative. So you do have to make this a minus, right? Got to make this minus. Now you just have to remember, what's the sine of 30 degrees? Can you all remember the sine of 30 degrees? That's one you need to learn. 30 degrees is pi over 6 in radians, but what's the sine of pi over 6? What'd y'all say? 1/2, right? It's 1/2. So just put a minus there. So there is, there's our sine. 210 is minus 1/2. What about the cosine of 210? So that's plus or minus the cosine of 30 degrees. Is it plus or is it minus? It's minus, right? Because again, in the third quadrant, cosine is also negative. So let's see, what's cosine of 30 degrees? Square root of 3 over 2, right? So see how quickly we got that? Yeah. Jad, just remember, sine is associated with the y-axis. So if the y-axis is negative at where an angle is, the sine is going to be negative. And cosine is associated with the x-axis. So if the x-axis is positive where an angle is, the cosine is going to be positive or negative, right? And then tangent is sine over cosine. So if you know the sine of the sine and the sine of the cosine, then you can figure out what the tangent is supposed to be. All right, let's try one more here. Let's try, and then I'll let y'all try some. So there is 630 degrees. Okay, so I've already drawn a picture of that. That's pretty big angle. So in 630 degrees, you have one full revolution. That's 360 degrees. And then to get to 630, you have to go another 270 degrees. Did I do my calculations right there? So if you take 360 plus 270, that's 630, right? So you go 270 past one revolution, and that brings you over here, to the negative side of the y-axis, right? So that's what 630 degrees looks like. So what does the reference angle look like? Here you can draw the reference angle two ways, but either way is the same. If you want to, you can draw it up in this direction. Remember, you have to draw it positive. So between the terminal side and the x-axis. You could also draw it here on the left-hand side. But it comes out the same either way. What is the reference angle? What? 90 degrees, right? Yeah. So reference angle is 90. So whatever happens for 630 is going to be essentially what happens for 90 degrees, right? So the sine of 630 degrees is going to look like the sine of 90 degrees, right? Except is do we have to adjust the sign? Yes, because we're down here on the negative side of the y-axis, right? So this is minus. And what is the sign of 90 degrees? Yeah, sine of 90 degrees is 1. It's the square root of 4 over 2. Yeah, look at the front half of that table. See it for sine? Yeah, you can also do it from the unit circle, but you can also do this table. Remember, for sine, Emil, it's square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, up to 90 degrees, square root of 4 over 2, which is 1.
Yeah.
Right.
The unit circle kind of, no.
Okay, so we end up with minus of that, which is 1. What about cosine of 630 degrees? Well, that is that plus or minus, or this is called the law of the excluded middle. It's actually neither, right? Okay, because you're right there on the y-axis, and at that point, the x-axis is neither positive nor negative. Okay, so you can just forget about the sign. Actually, it's the same as the cosine of 90 degrees. What's the cosine of 90 degrees? 0, right? Okay, so okay, guys, I'm gonna let y'all do some. I've got 3. Can I squeeze them into the picture here? All right, so I've got some graph paper. I can give you graph paper, but we got 3 to do, but let's do them one at a time. So let's start with the first one, which is 2 pi over 3. That one should be pretty easy. So what you want to do is draw the angle, and then draw the reference angle, and then write down what the reference angle is, right? So so what is theta bar in this picture, and then use that to compute the sine and cosine of 2 pi over 3. We just did this a moment ago, so you should without reference angle, so you should remember that. Anyway, you can check your answer, by the way, with your you can check your answer with your table, right? Because 2 pi over 3 is in that table. All right, so I'm gonna give you graphing paper. Yeah, you can scribble in your notes. It's not really necessary to have graphing paper to do this. Better to scribble it down. Actually, I have. I'm also going to pass out. Okay, sure. So that's your. Now that's right. Bar six. Right, bar six. And draw this one. That's all right. So that's the now the rectangle is showing. So what's that? All the process. Your number is. Mom, you have the same issue. Your number is, you should be signing 16 on 16. Oh, on the roll sheet, always sign in 16. Okay, let's see what we did here. So on at least the first one. Okay, so let's see if we can draw 2 pi over 3. If you're having to think about this in degrees, that's fine. Okay, that's fine. That certainly makes it easier to, I think, to draw accurately. 2 pi over 3, by the way, is 120 degrees, right? If you convert that to degrees. So 120 is going to be a little bit past 90, right? It's right there. Okay. You can also remember that pi over 3 is 60. So if you do 2 pi over 3, that 60 would be here, and then another pi over 3 is another 60, right? So that would move you slightly into the second quadrant. So that's the original angle theta, but we want to find theta prime. So to theta bar, right? So to find theta bar, you go between the terminal side and the x-axis always. So there is what theta bar is in this picture. So if this angle is 120, then this piece left here down to the x-axis would be what? 60, right? Okay, because a full open angle, right, half a revolution is 180. So if this is 120, then this piece must be 60. So so it's 60 degrees, or you can write it in radians as pi over 3, right? So so we know now that now we're really in good shape, right? We know the sine of theta is going to be something like the sine of pi over 3, but we may have to adjust the sign. But we don't have to adjust the sign here because we're in the second quadrant and sine is positive in the second quadrant, right? So we can just take the sine of pi over 3, which I think is square root of 3 over 2, isn't it? So so the sine of 2 pi over 3, right, is square root of 3 over 2. Now, again, people were asking me about remembering sine and cosine for special angles. One trick that I reminded people of, right, is remember in this chart, sine begins at 0, right? Which is the square root of 0 over 2. And then the next special angle is 30 degrees. Sine counts up. So it's the sine of 30 degrees is square root of 1 over 2, which is 1/2. And then 45 degrees, the sine is square root of 2 over 2. Then the next one is 60. Sine of that is square root of 3 over 2. And then 90 degrees, the next special angle, the sine of that is square root of 4 over 2. See, it's always square root counting up over 2. Square root of 4 over 2, though, is 1. All right. For cosine, it counts down. Cosine of 0 is square root of 4 over 2, which is 1. And then for 30 degrees, it's square root of 3 over 2. For 45 degrees, it's square root of 2 over 2. For 60 degrees, it's square root of 1 over 2. And then to 90 degrees, it's square root of 0 over 2, which is 0. So there's another mental trick for remembering sine and cosine for your special angles. All right, did y'all try 11 pi over 6? All right, so try that one. And then also minus 5 pi over 4. All right, so 11 pi over 6 then minus 5 pi over 4. But please remember, this scheme works for any side, any angle. It doesn't have to be special angles, right? Okay. So 11 pi over 6 is a special angle, and so is 5 pi over 4. But this idea works for any size angle, not just special angles. What does 11 pi over 6 look like anyway? And what's the reference angle for that? What does minus 5 pi over 4 look like? And what's the reference angle for that? Sometimes it's tricky for negative. Reference angles are never negative. Remember, they're never negative. So you always draw them positive. Let me watch on. Yeah, the reference angle, always draw it to the x-axis, even if the tendon to draw it to the y-axis, rise to x-axis. Oh. I know it's hardest. Oh, no. No, you do it right. I really. Hour 6. Your conversation is 30. Almost 6. Small hours. Small hours. Oh. And yeah, now make sure you get that. Sure you got some. All of those sides. 20%. Yeah. Yeah, kind of. Yes. Because, yeah, because sine cosine are always. Yeah, I'm very correct. You don't have to, but it's helpful. It's really going to be helpful if you're not dealing with special cases. Okay, let's go look quickly at these two before we take our break. So even if you didn't do the F, we'll go ahead and do that one. All right. So 11 pi over 6. One way, if you want to convert that to degrees, that may be really easy for you because that's going to be 330 degrees. So it's easy to understand 330 degrees, right? That's going to be almost 360, right? But not quite. So it's not quite one full revolution, right? And so this is going to be the reference angle. This little piece between the terminal side and the x-axis is the reference angle. And of course, that obviously would be what then? What's left here? Yeah, that's, yeah, 30 degrees, right? So your reference angle is 30 degrees. So you know that the sine of 11 pi over 6 is the same as the sine of 30 degrees, except you have to adjust the SIGN, right? Because in the fourth quadrant, sine is negative. And then you just have to recall, oh, what is the sine of 30 degrees? And I think it's, isn't it 1/2? So you end up with minus 1/2. Another way of thinking of this, though, if you really want to get daring with your radians, remember pi over 6 is 30 degrees, right? So if you start counting off pi over 6s, let's just do it. There's 1 pi over 6, 2 pi over 6, 3 pi over 6 would bring me up to the y-axis. 4 pi over 6, 5 pi over 6, 6 pi over 6 will bring you back to the x-axis. 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, almost to the almost one full revolution. Just missing pi over 6 or 30 degrees being one revolution. What about the cosine here? So cosine of 11 pi over 6 is the same as the cosine of 30 degrees or pi over 6. And there you don't have to adjust the sign, right? Because cosine is positive in the fourth quadrant. So you get the cosine, which is that square root of 3 over 2? Okay. What about now minus 5 pi over 4? Here we have to draw a negative. So let's start drawing that minus. And again, if you want to convert that to degrees, that is, what is that? Minus 225 degrees? Is that, no? Is that right? Yeah. Okay. Or if you want to, you can count off in radians. Remember, pi over 4 is 45 degrees. So if we're going to count off 5 of those, we would do what? Remember, we're going in the negative direction. So there's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. Oh yeah, that's right in the second quadrant. So there's our original angle. So the reference angle is this angle. Don't draw it to the y-axis. Back to the x-axis in the positive direction. So the reference angle is what? 45 degrees, right? Or pi over 4. So the sine of minus 5 pi over 4 is the same as the sine of pi over 4, except we may have to adjust the sine, right? Do we? No, I don't think so, right? Because we're in the second quadrant, right? So we just get what? Yeah, square root of 2 over 2. And then the cosine of minus 5 pi over 4 is cosine of pi over 4, except here now we do have to adjust the sign, right? Because in the second quadrant, cosine is negative. So we get what? Minus the square root of 2 over 2? There we go. Nice. So see, don't need a calculator, get exact results here, right? I have one more there, so we'll look at this one when we come back. So let's come back at about 11:30, and I will show you minus 7 pi over 3, but now y'all are all really good. So this one's should be fairly easy for you. Minus 7 pi over 3, though, remember that's going to be more than one revolution, right? Because 6 pi over 3 is already 2 pi. So this is already one revolution. Okay. Okay, let's try this one. And then we're going to use this to, we're going to use our knowledge now to help us graph a curve. All right, so just one more here. Suppose theta is minus 7 pi over 3. Okay, so if you can convert that to degrees if you like, but you can make a pretty good stab at drawing this without converting this to degrees, because minus 7 pi over 3 is that's got contained in it minus 6 pi over 3, right? Minus another pi over 3 would give you minus 7 pi over 3. But this is already minus 2 pi, so that's one revolution. So what you're really doing is just going pi over 3 past one revolution, right? So if you draw a picture of that, there's the, let's be sure we draw it in the right direction though. So it's negative, right? So we're going to draw clockwise. So there's one revolution, that's minus 6 pi over 3. And then to get to minus 7 pi over 3, we're going to go another pi over 3, right? So that is about another 60 degrees into the fourth quadrant. So the reference angle is here, right? Remember, reference angles are always positive. So you would draw the reference angle back up to the x-axis. Of course, how much is that then? Remember, we went pi over 3 past one revolution, correct? So how much is this? Pi over 3, right? So your reference angle here is pi over 3, okay? And so then it's right, very easy, right, to compute sine and cosine. So the sine of minus 7 pi over 3, right, is going to be minus the sine of pi over 3, because we're in the fourth quadrant. Sine is negative, fourth quadrant. Sine of pi over 3, though, I think is square root of 3 over 2, right? So we have minus square root of 3 over 2. And then the cosine of minus 7 pi over is just the cosine of pi over 3, right? Cosine is positive fourth quadrant, so we don't have to adjust the sign. And the cosine of pi over 3 is 1/2, right? So there's our sine and cosine. What if I gave you a reference angle, a weird reference angle like this, and I ask you to find the, I'm sorry, a weird angle like this, and I ask you to find the reference angle. So suppose I said theta is 5. What's the reference angle? Well, is it radians or what is it, Emil? Yeah, but I'm asking you back because you know the answer, right? Which is it? It's radians, right? Amanda, why do we know it's radians? then your perspective is exactly correct, right? It does not have sun, right? So that is radians. So this is 5 radians, kind of a weird number of radians, right? It's not a multiple of pi. All right, we're used to seeing pi in our radians, but that's all right. Okay. So how would we find the reference angle? Well, you know, you're gonna have let's draw a picture of this. So this is positive, right? So this angle is opening in the positive direction. If it went to here, how much would that be in radians? That's pi over 2, which is approximately how much? So your calculator is going to help you here, right? Well, what's pi over 2? What? About 1.57, right? Okay, approximately. Pi is an irrational number, so this is not exactly 1.57, but close. So we're certainly past that, right? If we come up to here, that would be pi. Well, you know approximately what pi is, right? That's what? Yeah, that's 3.14. So we're going to go a little bit past the 3.14, right? Okay, but probably not all the way down to the y-axis, because that is 3 pi over 2. And how much is 3 pi over 2 approximately? So again, you have to have your calculator help you here, right? What? 4.71? Ah, okay. Oh, so we are past that. All right. Oh, I was mistaken. I thought we were past that. So we are going to get past that a little bit, right? Somewhere into the fourth quadrant. Okay. So there's our angle somewhere over here in the fourth quadrant. We know we're not going to make it to 1 full revolution, because how much is 1 full revolution? That's 2 pi, which is approximately what, 6.28? So somewhere between 3/4 of a revolution, right, and a full revolution. There's theta equal 5 if you drew it. So here is the reference angle then. So how would you find the reference angle? Yeah, you go up to the x-axis, right? So Ravi, how do I on paper go up to the x-axis? Yeah, but I think you said it backwards. To get this, you would subtract the 5 from the 2 pi, right? Okay, the 2 pi is going to be bigger than the 5. Yeah, okay. So your reference angle here is exactly 2 pi minus 5, right? Okay. So that's going to be approximately 6.28 minus 5, right? Okay, or about 1.28, right? But here it is. There it is exactly. Okay. Wow, I wonder if that's right. Let's try that on the calculator. So on your calculator, compute sine of 5. Make sure you're in radian mode, and then compute sine of 1.28. See if they come out to be approximately the same, except for the sine, right? They're the same, okay? Except the sine is going to be different, correct? Because I just said compute the sine of 5 and also the sine of 1.28. They should be the same except for positive or negative, right? Yeah, the sine of 5 is negative, right? Sine of 1.28 is positive, though. Except the SIGN will be on, right? Positive or negative will be different, though, right? Yes. Okay. Okay. Now, now that we have this knowledge here of computing sine and cosine for arbitrary size angles, see what this is going to allow us to do now is to think of the trig ratios as functions, not just as ratios of sides of a triangle, but as functions of numbers. And so we can graph them like that, okay? So that's what we're getting ready to do. We're going to graph now the sine function. We're going to think of this as a function of x. But I got to caution you, our inputs here are going to be, of course, they're going to be values along the x-axis, but they're going to be in radians, all right? So we're going to assume the x-axis is real number radians. So to graph the sine function and get the famous sine curve, which is what we're getting ready to create now, okay? That's what we're going to do. So so we're going to do this by plotting points because we don't know what the sine curve looks like, right? So we don't know what to expect here. So we have to plot some points and then see if we can connect our points with a smooth curve. So I want to plot lots of points. So I need to have people help me with this because we're going to fill out a table. Okay. All right. You see this table we're going to fill in, and then we're going to plot these points. Oh, right here. Yeah. Okay. Well, that's going to minimize it, but I don't want to keep it. I don't want it to be minimized. All right. So here's what I want y'all to do. I need the class for me. So the people who are physically, I want you to fill out for me this first table. Okay. So you're going to compute sine of 0, sine of pi over 4, etc. Right? Okay. Up to 2 pi. Okay. So in other words, for 1 revolution, I want you to compute the sine, and then we're going to plot those numbers along this coordinate system, right? Okay, so y'all know you're just going to fill in this column. Make sure you give me a decimal approximation, though. You can give me the exact value in many cases here, though, but I need a decimal approximation because I got to plot these numbers, right? And for you guys at home, I want you to do it. You got the little bit harder task. If you feel at home, hear me. You need to fill in this column for me. So you're going to compute sine of these values, right? Okay. These are negative x values so that we can plot the left half of the sine function. All right, so we're going to treat sine now as a function. We're going to input an x value and we're going to get a matching y value. And we can do that now because we can compute the sine for any size angle, correct? Right? So we're not just limited to angles between 0 and pi over 2. So we can actually plot this sine function for the entire x-axis. Well, of course, I can't plot the entire x-axis, but I'm going to plot this much of it and see if we can see a pattern in the curve. Okay. All right. So y'all start filling in those values. So the class has, how many is that? 1, 2, 3, 4, 9. And then I don't know how many for the people at home, right? Fill this in for me because I'm going to ask you to, I'm going to write them down here in a second after you've had time to use those. You can look at your table if you want to, but remember, I need a decimal. I need a decimal, or you can use your calculator too, but I need a decimal approximation, right? So I can actually plot the numbers. Square root of 3 over 2 is great, right? But I need to convert that to decimal before I can plot it. Some of these are easy because I know what sine of 0 is, right? That's already, I know that's 0. So y'all can fill that one in fast. Okay. So just a few minutes there. Plot these, compute these quickly. So you guys at home, I'm depending on you. I got to fill in this table for me, right? So you can use, it's fine to use your calculator. Make sure you're in radian mode. Make sure you're in radian mode. Now, these all we could calculate exactly, but you can use your calculator here. Just make sure you put the negative in front of your angles. Some of these I can fill in easily. I think that one is 0 and that one is 0 also. Yeah, I don't have to make the plot. I'm gonna make the plot, so y'all just have to fill in these tables. Are y'all still computing these? Ishan gave me some numbers. Okay, Ishan, we'll keep those. We'll keep those in mind. Okay, let's start trying to fill in some values here and see if we can plot these. See how good of a plot we make. We'll compare this to the computer generated plot and see how good our plot is in a second here. Let's start with pi over 4 though. What's the sign of pi over 4? So I know that exactly, right? It's square root of 2 over 2, but what is that in so about 0.71? Okay. What about sine of pi over 2? That one we know. 1, right? Okay. 2 pi over 3. 0.87 about, right? Okay. Pi back to 0. 7 pi over 6. Negative 1/2, right? Negative 0.5. Okay. 3 pi over 2. Negative 1. 5 pi over 3. So that is minus 0.87. So that must be minus the square root of 3 over 2, right? Which is about minus 0.87. And then 2 pi is 0 again. Okay. All right. So let's see if we can plot these points kind of closely. It's hard to do by hand over here, but so for 0, okay, that one is not hard, right? There's 0, right? Pi over 4 would be right here, and that's about 0.71. I'm guessing 0.71 is maybe about right there. Pi over 2 is up to 1, right? So pi over 2 is up here at 1. And then at 2 pi over 3, so here's about 2/3 of pi, I'm thinking. That's what? 0.87? That one's really hard to locate, right? And then for pi down back to 0, right? And then 7 pi over 6, maybe about right here. That's gone down to -1/2. Am I doing that right? And then at 3 pi over 2, it's down to -1. And then at 5 pi over 3, what about -0.87? Maybe about right there. And then at 2 pi back to 0. Okay, so let's try to see if we can connect these with a smooth curve, and you get this nice oscillating shape here, right? And that nice oscillating curve like that is called the sine curve, okay, or the sine wave, often called the wave because it's so wavy like that. And of course, you know, as you go past one revolution, right? This is from 0 to 1 revolution. Of course, if you go past 1 revolution, you just repeat this pattern, correct? Right? Okay. So so this curve is just going to repeat over here, just like this, to the right indefinitely. So I didn't draw it very well repeating, okay, but it's this shape, right? Just duplicated every 2 pi units to the right out to positive infinity, right? That is the sine curve. So the sine curve is really great now for modeling quantities that oscillate like this. And in practice, there are lots of quantities that oscillate like this one, okay? All right, many quantities have this pattern, right? Where they increase and decrease, right? In this wave pattern, right? Over time, all right? And so the sine curve and cosine, very useful for modeling such quantities. What about the negative side here? Okay, I think it's going to also look like the piece from 0 to 2 pi, just copied over to the negative side of the x-axis, right? Because here we're just going -1 revolution, right? Okay, so we're essentially just going to duplicate what we had with 1 positive revolution, but over here on the negative side. Let's see if that's correct. So Ishan says for minus pi over 3, this is about -0.87, and then -1, and then -0.5, and then 0. And then here we're at 0.87 again, and then here we're at 1. And then what, 0.5, 1/2, and then back to 0. Okay, so let's see if we can plot those. Let's see, pi over 3, maybe about right there, correct, that's the -0.87, maybe about right here. And then at minus pi over 2, we're all the way down to -1. And then at 5 pi over 6, we're maybe about right there. We're back up to -1/2. And then at minus pi, we're back to 0. And then at 4 pi over 3, we're up to 0.87, not quite up to 1. And then at 3 pi over 2, we are at 1. I didn't read this one very good at all. Let's erase this a little. So at -4 pi over 3, about up here at 0.87, that's a little bit better. And then at -3 pi over 2 at 1, and then at 11 pi over 6, back down to 1/2, and then at minus pi over 2 back there, right? So that looks a little bit cleaner. There's kind of the left side of the sine curve. But again, it just repeats here in this oscillating, wavy, ripply pattern there indefinitely to the indefinitely left. So in a sense, it's an easy curve because you know, it just sort of repeats itself, correct, right? But in another sense, it's a complicated curve because it's wiggling a lot, right? Okay, it's increasing and decreasing from left to right frequently. Okay, so it's got lots of peaks and valleys in it. So that in that sense, it's a little bit complicated. Let's see what the computer shows us is the graph of the sine curve. So I've got this graph now with graphing software, if I can get hold of it, called Desmos. And we're going to use this sometimes for graphing, just because it's free and convenient. And very easy to use. So there I just typed in there's the expression for the sine function, y equals sine of x, and there's the graph of it. Okay, so we did a pretty good job of graphing that, right? Notice that what's the range of the sine function, the range. So what output values, what y values can you get from the sine function? What now? What output? What y values? What's the smallest y value you can get? -1, and the biggest one is 1. Yeah. So the range is -1 to 1, right? What's the domain though? All real numbers, right? So the domain is all real numbers. That's what we just went through the trouble of figuring out how to find, how to compute sine for large numbers and small numbers, right? So the domain will be all real numbers, but the range is very restrictive, just -1 to. Okay, if we throw in here the cosine curve, see if I can type that in. So if we throw in here the cosine curve, you see it looks very similar. And I'll tell which one is the cosine. They're both graphed in red. This one is the cosine. Okay, all right. Sort of the slightly thicker one is the cosine, because cosine of 0 is what? It's cosine of 0? 1, right. So cosine of 0 is 1. So this is how you can see this is the cosine curve, right? So it's almost got the same shape, right? Actually, it's got the identical shape to the sine curve, right? Okay, it's just shifted slightly, all right? However you want to think of it, to the left or to the right. Okay. Well, we are gonna spend some time studying curves of sine of the trigonometric functions. These are called sinusoidal curves. And so we're going to learn a lot about their graphs because these sinusoidal functions, these sinusoidal curves, again, are very useful in practice and helping us model real world phenomena. Okay, so we do want to learn a lot about these functions. Before we do that, though, we need to spend a little bit of time introducing some more terminology related to functions, because these functions, again, are a little bit more complicated than, just straight lines, right? Before we do that, though, let's finish off today. I want to show you some important, what are called identities. So these are equations that are always true for the trigonometric functions. And there are lots of such identities, okay? I'm only going to introduce at this point some basic ones, and that are really useful, but there are others that are important as well. Okay, so the one that we've already learned is that how to compute tangent, right? Remember, tangent of an angle is always sine of the angle divided by the cosine angle. Okay, so that's a very important identity. The book lists these as identities, but you already know these things, right? Cosine is the reciprocal of the sine, secant is the reciprocal of the cosine, cotangent is the reciprocal of the tangent, right? Likewise, cotangent is cosine divided by sine. But now that's useful, but not as useful as remembering that tangent is sine over cosine. This one you can easily reproduce because you know that the cotangent is the reciprocal of the tangent, right? So whatever the tangent is, you flip that and that will give you the cotangent. Now, these next group of identities here, these are especially important. These are called the Pythagorean identities. And it's the first two that are used most frequently. This one's not used as much. All right. So again, these are called the Pythagorean identities because they kind of look like the Pythagorean theorem. In fact, they're related to the Pythagorean theorem. Right. The first one is really important. Notice this one. So this one you're going to have to remember because this comes up all the time. If you take an angle and a sine of an angle and square it plus cosine of that same angle squared, that always adds up to 1. So sine squared plus cosine squared is 1. You'll always hear that this identity mentioned in that way. Sine squared plus cosine squared equals 1. Now, related to that is a second Pythagorean identity. And this one is also very useful, but not as useful as sine squared plus cosine squared equal 1. This one becomes important in the second semester of calculus, though, all right? Really useful in the second semester of calculus. The book expresses it in a kind of a weird way. So they say tan squared plus 1 is equal secant squared. I always like to write it this way, though. Secant squared minus tangent squared equals 1. So see, these two sort of look alike, right? And again, they're both referred to as Pythagorean identities. So remember, secant squared minus tangent squared equal 1. Sine squared plus cosine squared is 1. Secant squared minus tangent squared also equal to 1. This identity is really related to this one. This one we don't use as frequently. So these are kind of 3 facts that you sort of want to remember or memorize, right? Because they become useful in many situations. This one especially useful. This one you will use a lot. This one less important, but in the second semester of calculus, this one becomes really helpful. Let's look at this example and see what they're asking us to do. So these are going to refer to these identities. It says express cosine theta in terms of sine theta. So we want to write down what is the cosine theta, but we want to write an expression that only involves the sine. Okay. So how can we do that? I think we can do that from this identity. Okay, I think we can use this identity because take that identity, sine squared theta plus cosine squared theta equals 1 and solve that. Let's solve that for cosine. Oh, by the way, do you know, maybe I didn't mention this. Sine squared theta is the same as sine of theta squared. Okay, all right. But we often write this expression with the exponent above the sign, but it means the same as taking the sine of theta and squaring it. So cosine squared theta means the same as taking the cosine of theta and squaring it. All right, let's see if we can take this. Let's see if we can take this equation and solve it for cosine. So how would you solve that equation for cosine? What would you do first? So we want to get cosine theta equals something. What would we do first there? Yeah, subtract the sine squared, right, from both sides. So you would get cosine of theta squared is equal to 1 minus, right, sine of theta squared. Now we should be easily able to solve that for cosine, correct? How can you solve that for cosine now? Just take the square root, right? Okay, so that's what we're going to do. Just take the square root. But now, Amanda, when you take the square root, I'm going to put the square back with the sign, so I don't have to write the parentheses. That's the point of putting the 2 above the sign, so you don't have to put parentheses there. But now, Amanda, when you take the square root of a number, remember, how many square roots do you get? 2, 1 positive and 1 negative. So be careful that you include both possibilities. So there it is. There we did it. There is the cosine of theta written in terms of the sine. See, this expression only involves sine, right? Okay. And so there you have cosine of theta computed in terms of the sine. Let's see what the second one says. Express tangent of theta also in terms of the sine, okay, but where theta is in quadrant 2. So they're going to tell you something about theta here, telling you theta is in quadrant 2. Well, we don't need this information immediately. We'll save that for the end. So express tangent in terms of the sine. So you want tangent equal, and then you want some expression that just involves sine. Okay. Now let's start off with our basic identity. We know tangent in terms of sine and cosine, right? What's the tangent in terms of sine and cosine? It's sine over cosine. So we can write this down to begin with. Unfortunately, that doesn't have just sine in it. That has cosine in it. I want tangent written just with a sine. But now, Emil, how can I get rid of the cosine? I have this previous problem, right? Because don't I know that cosine is this from the prior problem? So where I have cosine, I can write plus or minus that square root, right? So you have sine of theta over, unfortunately, you got this plus or minus in it. So plus or minus 1 minus sine squared of theta. But now here's where the information they're giving us about theta is helpful. They told us what? Theta is in quadrant 2, right? So we know that what's the sine of the tangent in quadrant 2? Sine of the tangent. Remember, when you compute the tangent, you pick this point, right, off of the terminal side, and then you do what with the y and the x? How do you compute tangent from that point on the terminal side? No, what? Remember, what's the original definition of tangent from this picture? Y over x, right? But that's going to be, what's the sign of that going to be in the second quadrant? What's y over x going to be? Yeah, in the second quadrant right here. Y is what sign? And x is what? So altogether, this is negative, right? Okay. So if you're looking at this fraction, do I want plus there or minus from the bottom? Yeah, I want the minus, right? Because I've got to make sure this whole thing is what? Negative, right? So you can just forget about the plus sign. The minus sign is what you want there. Now, you may say, but what if the numerator were negative? Because then I'd have negative over negative, which is positive. But sine of theta in the second quadrant will be what? Positive. So you have plus over minus, which is minus, which is what you want. Okay, you want the tangent to be negative. So there is the tangent written in terms of just the sine. Now, is that helpful? Probably not, right? Okay. When you want to compute tangent, if you only know the sine, well, it is possible to do that. Okay. So it is possible to take the sine and use that to compute the tangent. There's the formula for doing it. Okay. But I don't think you'll use could use that formula very much to compute the tangent, okay? But it's possible, all right? All right, so especially remember these two identities. Tangent is sine over cosine. I know y'all are going to remember that. Y'all, we've worked with that a lot, but also remember, especially this first Pythagorean identity. A sine squared of an angle plus cosine squared, it's got to be the same angle, is always going to add up to 1, right? Always going to add up to 1. Okay. Right, well, we've run ourselves out of time, I'm sure. What time is it? Oh, yeah, okay. All right, guys, so some of you I'm going to see Monday, right? People who need to come to class on Monday will be here with us on Monday, and the rest of you, I'll see you somewhere, okay? Either here or online. Remember, you've got a homework due on Saturday on solving right triangles. I think y'all can do that pretty easily now, I hope. Are you already finished that one? Oh, okay, all right. See, Emil finished it already. So, all right. So I'll see you guys on. I see you guys on Monday.